Hi everyone, this is another video on Chief Mate's ship stability past papers. A vessel of length 200 meters, displacement 65907.5 tons, kb 5.9 meter, kg 8.9 meter has the following equally spaced half ordinates of waterplane commencing from aft: 0, 10, 13, 14, 14.2, 14.3, 14.1, 14, 11.5, 6.2, and 0.2 meters, respectively. Calculate her change of trim if 500 tons of weight already on board is shifted 60 meters longitudinally. So whenever you come across a question which is asking to calculate change of trim, obviously you need two things: trimming moment and MCTC. So you can see that trimming moment is easily available, weight multiplied by distance by which it has been shifted, W into D, but MCTC is not available. So let me take you through some basics of longitudinal stability. There is a term called longitudinal metacenter. Longitudinal metacenter is different from the transverse metacenter. When we are dealing with transverse stability, vessel heeling and all, and there we come across transverse metacenter, transverse KM, transverse GM, but we don't put the letter T. If you say GM, that means it's transverse GM. But in longitudinal stability, when we are dealing with longitudinal metacenter like KML, we must put the small subscript L. Now let's see this diagram sketch here. It's a vessel on even keel. Center of buoyancy and center of gravity both are vertically in line with each other. Then as we go up and we find this ML, longitudinal metacenter. So how did this longitudinal metacenter, like in initial stability, it appears? Now vessel is on even keel. Let's say that there is a weight in the forward part and that weight is shifted aft by d meters. This will cause shift center of gravity also to shift aft parallel to the movement of the weight from G to G1. So earlier, center of buoyancy and center of gravity both were vertically in line with each other, but now they are separated. G has shifted to new position G1 and ship's weight is acting downward from G1 now, and center of buoyancy is still there, buoyancy force acting upward. They are separated by the lever GG1. So we have a trimming moment now, which is ship's displacement W multiplied by GG1. So as there is a trimming moment, the ship will start trimming by stern, and this will be the new stage. You can see now new waterline W1 L1, and the ship is trimmed by stern until the time the center of buoyancy again comes directly under center of gravity. G had shifted to G1, B, the center of buoyancy, will also shift to B1. Now again B1 and G1 both are in vertically in line with each other. Ship is again in equilibrium. So when we draw the vertical from the center of buoyancy, when she was on even keel, this vertical, and now in the trim stage, another vertical we draw upward. These two verticals intersect at a point called longitudinal metacenter. So the terms here are KML, then we have BML and GML. In order to find KML, we can add KB plus BML, and in order to find GML, we can subtract KG from KML. So KML minus KG will give GML. So now in this question, since MCTC is not given, how do we proceed? Step by step, I will just give you an overall view of the solution and then we do the solution. Trimming moment. As I told you, we require to find change of trim by the question, which is trimming moment divided by MCTC. Trimming moment is weight which has been shifted by d meters. So we have both values. We have 500 ton of weight and d is 60 meters. We multiply the two and we get trimming moment. For MCTC, we have a formula. The formula goes like this: MCTC is equal to displacement shift displacement capital W multiplied by longitudinal GM and divided by 100 into shift's length between perpendiculars. The shift displacement is given in the question. Length is also given. Now we need to figure out how to find GML. As I showed you in the sketch, GML can be found by subtracting kg from KML. And KML is nothing but KB plus BML. And now we are coming down to how to find BML. BML is given by moment of inertia, longitudinal moment of inertia about the transverse axis which is passing through center of flotation of the water plane divided by underwater volume. So moment of inertia, so that means now we are come down to finding longitudinal moment of inertia, or also it is called second moment of area. And this we will find using Simpson's rules. A simple sketch makes it easier. This is the sketch of the water plane, half water plane, because we have been given half ordinates. These are half breadths or half ordinates of the water plane. This is the aft part and this is forward part. So I have marked the ordinates, half ordinates rather, starting from aft. 0, 10, 13, 14, 14.2, 14.3, 14.1, 14, 11.5, 6.2 and 0.2. The length of the water plane is 200 meter and all ordinates are equally spaced. So what is the common interval h? Since there are 11 ordinates, so there are 10 equally spaced sections. So length of the shape 200 divided by 10 gives me 20 meters. So common interval between the ordinates h is 20 meters. Now you see there are two axes I have drawn. F is the center of flotation or geometric center or centroid of the water plane. And CD is a transverse axis which is passing through center of flotation. For calculating BML, I need moment of inertia, longitudinal moment of inertia about this axis CD, which is passing through center of rotation. But when we need to find moments, then we need levers. But at the moment, we don't know the location of center of rotation, so we cannot take moments about this axis. What we can do, we can draw a parallel axis either at the aft end or at the forward end. Like I have drawn at the aft end, a parallel axis AB is parallel to this axis CD, which is passing through center of rotation. Now the distances from this axis are available to us because we know common interval h, and all are equally spaced by h meters. So each ordinate, we can find the lever for each ordinate for taking moments from aft the axis AB. And since both the axes AB and CD, they are parallel to each other. So with the help of parallel axis theorem, we will find the moment of inertia about axis CD. Now let's go to Simpson's rule. There are 11 ordinates. So rule number 1 we can use. Make columns in tabular method, half ordinates, then second column with Simpson's multiplier, area function, then levers for moments, and then first moment of area function, then again the same levers because we need second moment of area, which is also called moment of inertia function. So we write all the ordinates in exactly the same manner as given in the question. I have written from aft end to forward because rule number 1 is applicable. So Simpson's multipliers will be 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, and 1. Multiply each ordinate with its corresponding Simpson's multiplier and write the area function. So every ordinate multiply by the Simpson multiplier and we get the area function. We write all the values of area function and now we write the levers because we are taking moments from aft perpendicular. Our lever AB, our axis AB is coinciding with the aft ordinate and 0 is the first ordinate from aft end which is coinciding with the axis. So of course the lever from that ordinate will be 0 because it's coinciding with the axis. Then second ordinate is h meters away, so 1h will be the lever. Then third ordinate 2h, then 3h, 4h, 5h, 6h, 7h, 8h, 9h, and 10h. The last ordinate, which is the forwardmost ordinate, so its lever from aft end will be 10h. H is, we know, 20 meters, we have calculated. So if I multiply 20 with 10, I get 200 meters. So which is the correct, because the forwardmost ordinate will be 200 meters away from the aft end. Now we have the moment function. This is first moment of area, moment function. So all the area functions are multiplied by their levers. And we write the moment function. So area function multiplied by the lever, we get the moment function. Multiply all the area functions with their corresponding lever and write down the moment function all the way up to the 11th ordinate. Now this is first moment of area. I need second moment of area, means moment of inertia. So once again I am going to multiply by the same lever. So same lever which I wrote down here is copied and pasted here. And now the moment function is multiplied by the lever again. So we get the second moment of area. And remember that there is an h here in the moment function and also h is there in the lever. So when we multiply it, we will get h squared. So all the values will have h square with them. So complete the table till the last ordinate. And now we take the summations. So area function, we add all them up and we get it right down here 339.8, which is summation 1. I call it summation 1. Then add all the moment function, first moment of area, add them up. We get 1630h. This is summation 2. Now add up all the moment of inertia function and we have 9792.4 h square. This is summation 3. Area will be, for Simpson rule number 1, h by 3 multiply by summation 1 and multiply by 2 because we have been given half ordinates So in order to get the total area of the water plane, we must multiply by 2. H is 20 by 3, and area function summation 1 is 339.8 multiplied by 2, and we get the total area of the water plane 4530.7 meters square. Now in order to get the location of center of flotation, so since we have taken moments from half perpendicular, so I can straight away get LCF. LCF is longitudinal center of flotation from distance from the half perpendicular, which will be simply moment function divided by area function. So summation 2, which is the sum of the products of all moment functions divided by summation 1, area function. So this is 1630H. So 1630H is 20 divided by area function 339.8, and I get 95.94 meter. This is the LCF, means distance of the center of flotation. The F is center of rotation formed of perpendicular. Now we come to the last column, which was moment of inertia column. Longitudinal moment of inertia about axis AB. So I is the symbol for moment of inertia, but this is the moment of inertia about the axis which is at half perpendicular, which I call AB, because we took our levers from half axis at the half perpendicular. So moment of inertia again with Simpson rule number 1, h by 3, then summation 3, the last column, and multiply by 2. Yeah, because we use half ordinates, so we want total moment of inertia. H is 20 by 3, then summation 3 is 9792.4 h square, which is 20 square, multiply by 2, and the value is 5,222,6133.33 meter raised to the power 4. This is the moment of inertia about aft axis, which is coinciding with the aft perpendicular. Now I will apply parallel axis theorem in order to get moment of inertia about the axis which is passing through center of flotation, CD. CD is the axis which is passing through center of flotation. So moment of inertia about axis AB minus AD square, where A is area of the water plane and D square is the distance between the two parallel axes. So moment of inertia about axis AB I have already here on top, 5,222,6133.33 minus total area is 4530.7, and D square, the distance between the two axes, is 95.94 squared. Once again, to remind you, this is this distance. This is our aft axis, and we got moment of inertia about this axis. Now we are finding moment of inertia about axis which is passing through center of rotation, and this D is the distance between the two axes, which is, we found LCF 95.94. So now I get moment of inertia about the axis passing through center of rotation of the water plane, which is 10523379.48. Underwater volume is displacement divided by the density of seawater. Seawater density is not specifically given, but you have to then assume 1.025 salt water. So displacement divided by density 1.025, I get 64,300 cubic meters. This is the underwater volume. And now the formula for BML. BML formula is longitudinal moment of inertia I about the axis passing through center of flotation, which is CD in my case, divided by underwater volume. So moment of inertia about center of flotation I get from here 10523379.48. Underwater volume is 64,300. So I get 163.66 meter is the longitudinal BM. KML is KB plus BML. KB is given in the question 5.9. BML we just found 163.66. So KML is 169.56 meters. And now we come to GML. Remember in the beginning when I showed you MCTC formula, I need MCTC and I need GML for that. So I am coming step by step towards GML. So GML is KML minus KG. I got KML here, 169.56. KG is given in the question, minus 8.9, 160.66 meter. This is now longitudinal metacentric height, longitudinal GM. Put this value here in the MCTC formula, displacement multiplied by GML upon 100L. Displacement is 65907.5, GML is 160.66, divided by 100 into ship's length, 200 meter. And what we get, 529.44 ton meter per centimeter, MCTC. Now the formula for change of trim is trimming moment upon MCTC. Trimming moment is W into D upon MCTC. W is the weight shifted 500 tons and distance is 60 meters by which the weight was shifted. So W into D and divide by 529.44 and we get 56.66 centimeters. Remember, whenever you use MCTC, which is moment required to change the trim by 1 centimeter, the answer will come in centimeters. So 56.66 centimeter. This is the final answer which was asked in the question. So you can go through these steps by step, the full solution, and understand how to handle this question. So basically, we need to know about longitudinal metacenter, which I explained to you using these two sketches here. Okay, thank you very much. If there are any questions, you can put in the comments and I will be happy to answer them.